All right, so yesterday we looked at graphs that were transformations of 1 over x. Today we'll look at graphs of a different format where there are linear expressions in both the numerator and the denominator. So the first thing is that your vertical asymptote is found exactly the same way, and that is from your non-permissive values. Because you have a denominator of x minus 2, we'll have a restriction on x that x cannot equal positive 2. So that's where our vertical asymptote is. At x equals 2. So we can put that in there. All right, now there's also a horizontal asymptote here. And to find the horizontal asymptote, it's not going to be the x-axis, because in this case, y can equal 0. A rational function equals 0 when the numerator equals 0. So you can set 4x minus 5 equal to 0, and you'll get x equals 5 over 4. Right? That is the x-intercept, where y equals 0. On the ones we looked at yesterday, because the numerator was a constant, there was no way to make y equal to 0. There was no x-intercept. And so the x-axis, or the line y equals 0, was our horizontal asymptote. That's not true for this one. So let's see where the horizontal asymptote is. We'll put the equation in our calculator and see what it looks like. So the numerator in brackets, 4x minus 5, close the bracket, divided by, open a bracket, x minus 2, close the bracket. So zoom 6, set our winners to their standard settings. And it looks like the y, or the horizontal asymptote, is above the x-axis. It's up here somewhere. If we go into our trace mode and just keep going to the left, you can see that the value of y appears to be approaching positive 4. Okay, appears to be approaching positive 4. And in fact, if we put a second equation in the line y equals 4, that certainly looks like that is the horizontal asymptote. If we try and find the point of intersection, second function trace, number 5 for intersect, enter, 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 there is no point of intersection. That's why it gives us an error. So this just confirms that our horizontal asymptote is at y equals 4. Now, here's how you can get that. If we look at the degree of the top and bottom, the degrees are the same, right? The exponent on x on the top is power 1, same thing as the exponent on x on the bottom. Both of these have the same degree. When that happens, you can get the horizontal asymptote by dividing those coefficients. The coefficients of the term that contain the highest power. So that'll be at y equals 4 over 1. The coefficient of the x on the bottom is 1. And 4 divided by 1 gives you 4. There's where the horizontal asymptote is. And you can use this step to determine the horizontal asymptote whenever the degree of the top and bottom are the same. Okay, so again, our graph, if we look at it, we can see that it's in the top right-hand corner and the bottom left-hand corner from the calculator. You could get that by choosing a point on either side of the vertical asymptote. So example, when x equals 3, f at 3 here will be 4 times 3 on top, which is 12. Take away 5 is 7. on the bottom. 3 take away 2 is 1. So it goes to the point 3 comma 7, which is up here somewhere. Again, what this does is it confirms that we're going to have an arm or a branch in that top right-hand quadrant. And then the other branch will be in that lower left, which we could confirm by finding the value of the function when x is something less than 2. Right? Maybe we might find the y-intercept, which we already talked about before, when x is 0. So when x is 0, you're going to get 0 take away 5, which is negative 5, over 0 minus 2, which is negative 2. So that's positive 2.5. When x is 0, y will be positive 2.5. So again, that just confirms that that branch is in that lower left-hand quadrant. And remember, our graphs always have arrows on either end. So this one actually does ask us to identify any asymptotes. We've already done that, as well as the intercepts. So here we found the y-intercept by letting x equal 0, 0, comma 2.5. We talked about the x-intercept earlier. Remember, that's where y equals 0 and a rational function equals 0 when the numerator equals 0. That's where 4x minus 5 equals 0, which is where x equals 5 quarters, 1 1/4. Right, so there's our x-intercept at the point 5 quarters, comma 0. If we wanted to state the domain and range of this, I'll use set notation, all values of x such that x cannot equal 2, because that's where our vertical asymptote is. And all of the real numbers are part of this. A range, all values of y such that y cannot equal positive 4. All right, so there's that graph. So for this next one, we'll graph it the same way. Starting first with our restriction on x. X cannot equal 4, so that's where our vertical asymptote is. Because the degree of the top and bottom are the same, we can find our horizontal asymptote. At y equals 2 over 1. You take the coefficients of those two terms that contain the highest power of x. So that's at y equals 2. So there we've identified our asymptotes. Let's find the intercepts of this graph. Our x-intercept is at y equals 0. Again, this is a rational function, and the rational function will equal 0 when the numerator equals 0. So that's where 2x equals negative 2 and x equals negative 1. That's the point negative 1 comma 0, which we can put on the graph. Our y-intercept is where x equals 0. So if we take the equation and let x equal 0, we're going to get 0 plus 2 on top over 0 minus 4 on the bottom. So that'll be negative a half. There's our y-intercept. So again, these 2 points just confirm that The one branch, again, is in that bottom left-hand quadrant. The other branch should be in the top right. We'll just confirm that by finding the value of the function at some number greater than 4, because that's where our horizontal asymptote is. So if we find f at 5, 2 times 5 is 10, plus 2 is 12, over 5 minus 4, which is 1. So that's the 0.5 comma 12. Again, this just confirms that the graph is in that top right-hand quadrant. And so there's the graphs. We've identified our asymptotes and our intercepts. If you're asked to state the domain and range, I choose to use interval notation here. It'll be from negative infinity to positive 4, and then again from positive 4 to positive infinity. I have to use the rounded brackets. And the range will go from negative infinity to positive 2, and then from positive 2 to positive infinity. All right? So that's how we graph these types of rational functions. So these ones are a little bit different. The biggest difference is that the numerator and denominator do not have the same degree. Right? It's similar to the ones that we looked at yesterday, where the numerator was a constant, but the bottom was a polynomial. So the degree of the bottom was greater than the degree of the top. And what we saw happen for all of those is that the x-axis was an asymptote, because once again, y cannot equal 0. Because the numerator is a constant, and the only way that y can equal 0 is if the numerator can equal 0. But it can't. It's a constant. Right? So, but this graph we're going to see is going to look a little bit different. We're going to graph y equals 1 over x squared. So we're going to graph f and g on the same grid. So that's what the first grid will be for. Now, f still has a non-permissive value of 0. Right? X cannot equal 0, because even if you square it, you still get 0, and you can't divide by 0. So we're going to have a vertical asymptote where x is 0, and a horizontal asymptote where y is 0. So what's different between this graph and the ones we looked at earlier today and yesterday is that in this case, no matter what value of x you choose, y is always positive, because you're going to square the x. So even if you choose negative values for x, when you square it, you're going to get a positive value. So this graph will always be above the x-axis. Y is always positive. And as x gets smaller and smaller, when you choose small values for x, let's say a half, and you square it, you're going to get a quarter. And then you got to go 1 over a quarter, which is 4. When x is a quarter and you square it, you'll get 1/16. And when you go 1 divided by 1/16, that'll be 16. So as x gets smaller and smaller, y is going to get larger and larger. It's going to approach positive infinity on both sides of the asymptote. And then as x gets larger and larger, like let's say x is 5, well, 1 over 5 squared will be 1 over 25. It's going to get smaller. When x is 10, 1 over 10 squared is 1 over 100. It's even going to get smaller. It's always going to be positive, but it's going to approach 0. So this graph is going to look something like this. Both of the arms are above the x-axis, because y is always positive. So this is the base graph, 1 over x squared. Now, g we can write as a transformation of 1 over x squared, and here's how. we can say that g at x can also be written as 3 over the denominator is a perfect square trinomial. The factors of that are x minus 5, or x minus 5 all squared. When you write it like this, you can see that it's a transformation of 1 over x squared. So comparing g and f, so g at x compared to f at x, you're going to have an a value of 3, because the numerator went from 1 to 3, which means you're going to have a vertical stretch. Always about the x-axis. By a factor of 3. As well, the x, which is squared, is now replaced with x minus 5. That's an h value. Remember, whatever happens to x happens to the x minus h. In this case, they're both in the denominator, and their h is hooked directly onto an x with a plus or minus. The x is squared, the x minus 5 is squared. So whatever happens to x minus h. It's in the denominator and it's all squared. So we're going to have an h value of positive 5, which will shift the graph 5 units right. Including our asymptote. Our asymptote will be at x equals 5. That's our non-permissive value. When x equals 5, the denominator will be 0. So, to do our new graph, again, we have that asymptote at x equals 5. It doesn't change the fact that the x-axis is an asymptote. And it also doesn't change the fact that this graph is always completely above the x-axis. Because no matter what x is, you're going to subtract 5, which might make it negative, but then you're going to square it. Have a good day. Now, it's true that there is also a vertical stretch, which means that the values of y get larger faster. But the shape is going to be the same. So there's the graph of f and g. Now, it does say also to compare the characteristics of the graphs of these functions. So if you're asked to compare, it's that. You talk about similarities, you talk about differences. And there have been questions on diploma exams in the written response where you need to compare. So you talk about similarities, you talk about differences. So we can say that f and g have the same horizontal asymptote. So this is one similarity. Right, that is the line x equals 0. Another similarity that these graphs share is that f and g is always greater than 0. They're both above the x-axis. So those are two similarities. Right? One difference we can say is that they have different vertical asymptotes. F has a vertical asymptote at x equals 0. G has an asymptote at x equals 5. Right, so there's a difference between the two. So now we're going to do the same thing in our second graph to compare f and h. So if we look at the equation for h at x, if we write it in the format that we're used to working with, that negative in front of the rational expression means that either the top or bottom is negative. Easier to make the top negative. And then the plus 6 moves to the end. So in this case here, you have an h value of -1. An a value, I should say, of -1. So that's going to cause a reflection over the x-axis. Then you're going to have an h value of -4 and a k value of +6. So that's going to shift the graph 4 left and 6 up. So the asymptotes will go 4 left and 6 up. But let's start with the graph of y equals f. Right, we're comparing to that. So that graph, again, has the x and y axis as our asymptotes. And as we've seen already, kind of what it looks like. It's completely above the x-axis. That's the graph of y equals x squared. And now for h, again, our asymptotes are changing because we go 4 left. Our vertical asymptotes at x equals -4 because we go 6 up. Our horizontal asymptote is way up at y equals +6. And remember, in this case, the graph reflected over the x-axis. So instead of going upwards, it's going to be going downwards. And you could confirm that if you wanted to by just do a little table of values like we've done in the past to find the values of y for values of x on either side of the vertical asymptote. Okay? If you're asked to compare these graphs, there really isn't much that the graphs have in common. The domain and ranges are different. The asymptotes are different. When we compared the previous ones, we talked about the fact that those two graphs were always above the x-axis. Y was always positive. That's not true for these two graphs either. There are lots of differences. Not really any similarities except that they're both curves. They're nonlinear. So f and h are both nonlinear. That's really the only similarity that we could state. Okay? They have different asymptotes and f is always greater than 0. H on the other hand can be less than 0. Not always. So let's say can be less than 0. So not much similarities except that they're both nonlinear. Lots of differences in the two equations. So same thing with this one. G and H are transformations of 1 over x squared. So we already know what 1 over x squared looks like. It has our asymptotes, the x and y axes. So we might as well draw it on both grids because we need to anyways. And now we're going to compare first f and g. So for g at x, compared to f, we have an a value of -1 again, which means it's going to reflect over the x-axis. And then the x is replaced with an x minus 3. That's an h value. So that's going to shift 3 to the right. Doesn't change the horizontal asymptote, but the vertical asymptote will now be at x equals 3. And again, the graph is reflected over the x-axis, so now this one's going to go downwards instead of upwards. And if we're going to compare, once again, we talk about exactly the same things. The only real similarity between these two graphs is that they're both nonlinear. They both have asymptotes. That's another similarity. But the asymptotes are different, so that's a difference as well. Our first graph is always greater than 0, and in this case, our second graph is always less than 0. So there's two differences between those two functions. Right? And when we work with the graph of h, again, I would factor the bottom. The factor there would be x plus 1 all squared, and then move the 2 to the end. So here we have an a value of 5, which means it's going to be a vertical stretch. And our vertical stretches are always about the x-axis. And that will be by a factor of 5. As well, our h value is -1. Remember, the value of h is always the opposite of what it appears to be. The general form is x minus h. Our k value is +2. So this graph will shift 1 left and 2 up. So our asymptotes are going to change because it goes 1 left One asymptote will be at -1, 2 up. The other one will be at +2. This graph is not reflected. It's just vertically stretched. So it just means the values of y will get bigger a little faster. So a couple similarities, they're both nonlinear. Both graphs approach positive infinity as you get closer and closer to the asymptotes. Differences, obviously the asymptotes are different. And the second graph is vertical stretched compared to the first. Okay, so those are some of the differences that you could talk about. All right. So on page 442, questions 2 and 4 is what you can work on for practice. So again, some of you still haven't handed in that review for Unit 3, exponents, exponential and logarithmic functions. So try and get that done and hand it in. So there's going to be a cutoff date for any of your missing assignments. It'll be probably sometime early in June. So I wouldn't leave a lot of that work till the end. It'd be a good idea to start working on that, getting that stuff handed in, because at the end of the semester, those blanks will be replaced with zeros, and your marks will go down. So go on Power School. If you see you have any missing assignments, dig them out, get them done, hand them in. If you have lost yours, I can get you another copy, but I just need a list of what you need me to get. But have a look first in your binders and see if you have any of that stuff. Okay?